Ana graduated from UC Berkeley with a degree in applied mathematics with a concentration in machine learning and data science. As you will see, those are pretty relevant degrees. She's worked at LBL since 2019 and has worked primarily with VRAP. She's recently started working on other projects, including one on natural language processing with Peter Thorkelson, and another for our water energy nexus work with Prakash Rao. Today's talk will focus on work related to V's research, just published in Fuel, the journal Fuel, on predicting physiochemical properties of molecules using machine learning. So with that, thank you, Ana, and take it away.
Thank you, Chris. Hi, everybody. Yeah, like Chris said, I'm going to talk a little bit about the paper that we just published in Fuel about using, machine learning to predict physiochemical properties of molecules. To help kind of illustrate our project and the work that we did, I wanted to start with a little scenario. Imagine that you saw, a picture of this beautiful cake on the screen, and you wanted to recreate it at home with the ingredients available on the right over there. Well, you may know right away that, radishes or lettuce have no business being in a cake. And depending on your baking experience, you can expect to need flour or eggs or sugar. But how much do you need of each? And do you need baking soda, baking powder? It's really not clear from just the final picture exactly what ingredients you have to use or what the best combine them is to get that final result. Well, with my research, we've been trying to predict physiochemical properties of molecules for aviation, and one of the biggest challenges was figuring out what features would result in accurate predictions, i.e., what ingredients go into the flash point or the heat of combustion of a molecule. And can we figure out a systematic way that will find those ingredients for multiple properties? Let's go a little bit into the specifics of the project. Properties of interest, or our cakes, were melting point, boiling point, flash point, yield setting index, and heat of combustion, which are properties that range from physical to complex. They are quite different from one another. We collected data from PubChem, Co-Optima, from other published sources out there, and we made sure that our molecules were applicable to biofuel and biofuel development specifically. And so we kept, only compounds including hydrogen, carbon, nitrogen, and oxygen. And we also wanted to make sure that the database was fairly, so we checked, furands, ketones, alcohols, aromatics, etc. Now, the ingredients that we had available were molecular descriptors. And these were generated with the help of Mordred. Mordred is this open source tool. It generates over 1,800 dimensional and three-dimensional molecular descriptors. And these can be things like number of oxygens or the first eigenvalue of the distance matrix. And they're grouped into families. So for example, number of oxygens is in a family with number of carbons and number of hydrogens. The problem with many ingredients is that too many descriptors can really increase the risk of overfitting and lead to really inaccurate models. It can also increase training time and it can increase storage need. So the meat of this project was really finding a way to get all of the appropriate molecular descriptors for each property. Once that was done, we used Teapot to train the models. Teapot is an automated machine learning tool that fits thousands of different pipelines and then just returns the optimal one for your data. So it does all of the model training and model optimization for you. Finally, we did develop an online tool where the models and data are integrated for ease of access, and I will show a couple of screenshots of that later so that everybody can see our pretty little tool. Now, like I said, we didn't magically come up with a way to identify what descriptors were good predictors for each property. It took a lot of iterations, and after a lot of pain, this is the process that we kind of landed on. The aim of feature selection is to maximize relevance of your features and minimize redundancy. So that's kind of what we try to keep in mind at every step of this pipeline. First, you have to get rid of any descriptors that errored out or that couldn't be calculated or that return non-numerical values, since those can't really be used as inputs in classical machine learning algorithms. Then we got rid of any descriptors that didn't bring in a lot of information. And that's where that variance threshold, that second little blue box came in, where we deleted any descriptors that had the same value for more than 95% of our molecules. After that, we wanted to minimize redundancy in the form of correlation. Correlation can be really problematic for certain machine learning algorithms. For linear regression, for example, it can lead to wildly varying and numerically unstable solutions. So before we're able to any model, we have to deal with these highly correlated groups of descriptors. For that, we used a Spearmint correlation coefficient, which calculates monotonic relationships. And so it would catch things like x and negative x squared, in addition to anything that was. And we found a threshold of 0.7 optimal. And this was done through a lot of comparing different thresholds and different coefficients and seeing which one gave us the best results. During this step, we looked into pairs of features, and if they were correlated by more than that 0.7 threshold, then we deleted one out of the pair. This was first done within each family of descriptors separately, since those tended to be more highly correlated. A lot of times they were, the same descriptor weighed by different metrics, and so those are going to be just easier to figure out that they're correlated. So we did the families separately, and then we combined all the features left from all of the families and repeated that step. And that results in, a set of non-correlated features, which is great, but we don't know how good of predictors they are and whether they're relevant for the prediction of our properties. So at that point, we used recursive feature elimination to rank features by importance. And that's that last light blue box that you see on the screen. Recursive feature elimination is an algorithm that assigns ranks to groups of features based on their importance for predicting the property. So features ranked 1 are considered to be the most important. Features ranked 2 are the second most important, and so on and so forth. And now that we have our features ranked by importance, the only problem is that we didn't know if, the top 10 features were enough to get good predictions, or if we needed the top 20 or the top 30. So at that point, we created different sets of descriptors. And that's that group features little step on that box over there. The first group included only rank 1 descriptors. The second group included descriptors ranked 1 and 2, and just sequentially adding higher ranked descriptors until that last group included descriptors of all ranks. And then at that point, we used Teapot, that automated machine learning tool, and we trained Teapot on all of the different feature sets separately to find the best model for each of these groups. And we ended up choosing the model and feature combination that yielded the best results. And then this pipeline was done for all properties separately. I know that got a little bit lost in the machine learning weeds, and there was a lot of just, these are all of the steps. But I mean, why do we care? Did it work? Here are some of our results. It's parity plots showing experimental versus predicted values for all 5 of our properties. And this is just for the test data, which means that the machine learning model has never seen this data. In general, our results show comparable or better performance than other published models, even with a bigger and more diverse data set, which we had. A couple of cool little quick things to note, for example, is melting point, which is that parity plot on the top left. Melting point has been historically hard to predict, and that trend, also showed up here despite having the largest database out of all of these properties. Another thing was that when evaluating the performance of different molecular families, we see that in general, our models predict hydrocarbons better than oxygen or nitrogen containing compounds, which is also something that has been, I mean, it's something that we've seen in other published literature. So a key advantage of these models, just apart from, the accuracy that they have, is that they can be easily interpreted. And that means that we can look at the feature importances of these models to kind of get an idea of what descriptors contributed the most towards the final prediction of each property. This can be useful in two ways. One, it can help corroborate the models by comparing what we see are the top descriptors to what we already know about the property and see if that makes sense. And two, we can use these importances to discover new relationships between properties and molecular structure. So for example, here are two charts showing the molecular as well as their for the boiling point and flashpoint models. Flashpoint and boiling point correlate really well. They can be used to predict each other. They have been used in the past to predict each other. And so it was not surprising that the top descriptors used in the flashpoint model, as well as their relative importances, kind of mimic those in the boiling point model. That was a good sign and kind of a way to gain trust in our models. These are the descriptors and the importance of the descriptors in the heat of combustion model. For heat of combustion, the most important descriptor was that ABC index, that really long blue line right there. ABC correlates with the stability of alkanes and the strain of energy of cycloalkanes. It's been used to predict the heat of formation of alkanes and cycloalkanes specifically. So it's kind of cool to see that in a more diverse data set like ours, which contained, furans, ketones, alcohols, this descriptor still popped up as the most important. It kind of suggested applications for the descriptor beyond what it is currently being used for. Finally, all of the data and our models have been integrated in this web tool that we've created. You can search the database and you can look molecules by molecular name, by InChIKI, by SMILES. If you're not quite sure what molecule you want, but you know that you want something with boiling point or yield setting index within a certain range, you can also filter through that. And you can choose to include our predictions from our models or just the experimental data that we have. And I have added the link to that cute little web tool up there on the screen so that everybody can go visit it if you want. Finally, I just want to say thank you to my team. Here are all of their smiling faces, as well as, Vito and Oak Ridge, who let us use all of their computing facilities to kind of train the models and do a lot of the machine learning pipeline on their servers. And with that, thank you so much for listening to me today. If you have any questions, I will take them now. Thank you.
All right. Well, thank you, Ana. I appreciate the presentation, and I definitely learned some stuff myself. So we have a question in chat from my colleague, Jessica Granderson. The question is, what was the starting point for this work in terms of what had previously been tried or methodological state of the art for predicting these properties? And then how did you come up with the approach you took here?
Oh, yeah. So there are currently other, machine learning models to predict all of these properties. Something that we wanted to achieve was specifically finding a process that would work for multiple properties. Since a lot of the other work focused on just one property, and it kind of included a lot of the previous knowledge about the property specifically. And so we wanted to see if we could find something that we could just systematically use for a lot of different properties. And then, sorry, the second part of the question was, how did you come up with the approach? Well, parts of it were kind of typical like feature selection steps. For example, removing anything that is non-numerical and that can't be used in a model, removing anything that gives you the same value for all of your samples. All of these are steps that are usually used in feature selection pipelines. And then, things like correlation, we knew that we had to deal with because it would mess up a lot of the models and the model training. And from that point, it was honestly a lot of trial and error and trying different types of feature selection algorithms and comparing results and seeing what worked best, what didn't. If we used a certain algorithm that come with caveats and other things that we need to auto check for. And so a lot of that was, trial and error, and also figuring out, given the data that we have, what made sense. I don't know if that answered the question or not.
Looks like it did. Thanks, Jessica. Any other questions from our audience? Feel free to use the raise hand feature under reactions, and be sure to unmute yourself before asking your question. Christian.
Yeah, great presentation. I was wondering about the good fit for the hydrocarbon family, and if there's any explanation for that, and also, is there a problem, given that I'm assuming you're looking at biofuels that might not be hydrocarbon based? Is there something about existing models or selections that kind of make that a better fit, because that might have been a more popular fuel?
Sorry, I'm not sure I understood the question. Could you repeat it? I got caught up for a second.
So in your graphs, your scatter plots, you showed that hydrocarbons had the best fit. Mm-hmm. Can you explain why that? Do you have a clue why that might be, and is that a problem, since you might be looking for biofuels that are not hydrocarbon based?
Yeah. Well, hydrocarbons, I mean, what we kind of found is that their molecular descriptors tend to more nicely explain flashpoint, because, for example, the flashpoint of a hydrocarbon is more clearly related to the length of the molecule. There's less complex interactions than there would be with molecules that contain oxygen or nitrogen. In terms of the second part of the question, and applying this specifically to biofuels and biofuel blends, we are now entering the second stage of this project, which is, instead of just predicting these properties for neat molecules, kind of using the technique that we've developed to do it specifically for blends, blends. But yeah, that's something that we're like actively working on right now. It's like almost a first pass of, can we use machine learning to predict these properties? And the answer is yes. And so now we're going into predicting them specifically for those blends of jet fuels.
Great, thank you.
So I raised my own hand. Thank you for the presentation. I had a question about the topic space here. When I read your bio at the beginning, you had obviously some background in data analysis and machine learning and data science kinds of issues. I didn't understand from your bio that you had much biochemistry or physical chemistry background. And so I'm wondering, A, did you need a lot of that background as you started this work? Or B, did you build that background as you did the work?
Yeah, it was kind of funny. I have very little chemistry, biology, biochemistry. I have very little background in that. I studied, only math. And so when I first came into the project, a lot of it was reading a lot of, organic chemistry textbooks, and teaching myself about molecular descriptors and exactly what they were, what they represented. It took me, honestly, like a long time to even realize that these molecular descriptors are grouped into families, that within each family we have the same thing weighed by different metrics. All of that I've just kind of had to learn as I go, which has been a lot of fun and really rewarding, but definitely something that at the beginning was really challenging for me.
I would imagine. Well, thank you. I think that's a great example of being able to bring one area of research and methodological expertise into a different area and derive useful results